So in this mini tutorial we're going to explore the nature of reactions at the carbonyl group. And these reactions are typified by nucleophilic addition reactions, that is, an addition reaction that occurs with nucleophilic attack as part of the reaction. So what is it about this group that makes it susceptible to nucleophilic attack? Well, essentially it's the fact that we've got the electronegative oxygen atom here that results in there being a partial negative charge on the oxygen and a partial positive charge on the carbon. And it's this partial positive charge that makes this part of the molecule susceptible to nucleophilic attack. This difference in charge is even more pronounced when we consider the resonance structure of this molecule, which looks like this, in which there's a full negative charge on the oxygen and a full positive charge on the carbon that makes it even more susceptible. So let's consider an actual addition reaction that occurs and involves nucleophilic attack. And as our nucleophile, let's use a molecule of water. And water is a suitable nucleophile because it has a couple of non-bonding valence pairs here. This can then, as a nucleophile, donate a pair of electrons as shown here. Then we see a movement of electrons here as well. And notice we're using full curly arrows here to note the movement of a pair of valence electrons. So this gives us a structure that looks like this, which isn't obviously our finished product. Just draw this out. We then see further movement of electrons here, and also we see a hydrogen ion here. So all together we then see the final product that looks like this. And what we notice is that we end up with our starting nucleophile, the water, being added across double bond. So we see OH being added here and H being added here. So taken together that's H2O or water. So that's effectively our starting nucleophile, the water, being added across our double bond. And this mechanism is similar regardless of the nucleophile that's attacking the carbonyl group. So let's just move the page down so we have a bit more space, and I can show you an example with another carbonyl group and a different nucleophile. So let's imagine now that we have a ketone to start with. So that's got two different alkyl groups attached. And let's imagine that our nucleophile now is an alcohol. Again, an alcohol can act as a nucleophile because it has the oxygen there with its non-bonding pairs. So again, the mechanism is the same as before. We see the movement of valence electrons here and here. So our halfway house, if you like, is then this structure. There's an alkyl there and an alkyl group there. Then we have there. And then our final product of the reaction is formed. And again, we're seeing the addition of our starting nucleophile, which in this case was a ketone being added across the double bond. So we started with the alcohol as the nucleophile. So you have part of it, the CH3O there, and we have the H here. So taken together, we have CH3OH, and that's the alcohol that acted as the incoming nucleophile. And the product of this reaction is called a hemiketal. So the outcome of the addition of an alcohol to a ketone is called a hemiketal. Now in practice, these reactions are usually acid catalyzed, so in fact the starting material is somewhat different. We see a hydrogen ion having come in to form this structure. And this actually makes the starting compound more susceptible to nucleophilic attack, because we see this group here, because the incoming acid withdrawing electrons more effectively to then give us this material like this, that again has a full positive charge on the carbon, so it just primes the carbon more effectively for attack by our incoming nucleophile.